What I want to spend a little bit of time on is talking about heterocycles. And these are compounds in which one or more members of the atoms are something other than carbon. Most commonly, that's going to be like nitrogen, oxygen, sulfur. There's some other ones out there, but those are the most common ones we see in OChem. And again, like if we were to replace one or more carbon atoms with something else, that's a heterocycle. And it is possible for these heterocycles to fit one of our three categories that we talked about in the previous video. There could be aromatic heterocycles, there could be anti-aromatic heterocycles, or there could be non-aromatic heterocycles. So they can still be considered these things as long as they fulfill the proper criteria. The tricky part is that most of these heterocyclic or heteroatoms contain lone pairs, and sometimes the lone pair is part of the pi system, meaning it counts for two pi electrons, and sometimes it doesn't. In that case, like carbon, it only contributes one pi electron. So I'm going to give you the simple rule to look at and determine that very quickly, and then I'm going to talk about why that is the case. So we're going to compare these two heterocycles. Now I'll kind of put the cart before the horse and tell you that both of these are aromatic heterocycles. So here's the short rule. We'll look at this one on the left first. Notice that there is a double bond already to the hetero atom, to the nitrogen there. If there is a double bond already to that hetero atom, then the lone pair is not part of the pi system. That means the nitrogen only contributes one pi electron, just like the carbons. And so this compound fulfills all of the aromatic rules, cyclic, planar, closed loop of p orbitals, and it has a 4m plus 2 number of pi electrons. So that makes this aromatic. Now, the other thing to look at is what if the heteroatom does not have a double bond to it already? In this case, it's going to contribute one whole lone pair. That's two pi electrons to the pi system. Now you look at this and say, well, that's a five-membered ring. That's okay. The number of members doesn't matter because it's about fulfilling the Huckel criteria, fulfilling those rules for aromaticity. So it's cyclic, closed loop of p orbitals. You say, well, wait a second, doesn't that nitrogen have to be sp2 hybridized? Think about that for a second. Is that nitrogen sp2 hybridized? What if I were to do something like this? Through resonance, what is that hybridization of that nitrogen now? It's sp2 hybridized. Go all the way back to one of the first few units of this semester. And remember kind of one of those golden rules of resonance. If you can draw a resonance form that shows an atom as sp2 hybridized, then that's what you counted. So this still fulfills all those rules. It has a closed loop of p orbital, all the atoms are sp2 hybridized. And if that nitrogen contributes its lone pair, notice how the resonance shows how it does that. I'll redraw this again. Notice that lone pair is going into the ring. And so there's that lone pair contributes two pi electrons, one for each of the carbon atoms, and that's a total of six pi electrons. So here, the lone pair is part of the pi system. And this compound as well is aromatic. Now, let me draw these kind of looking from the side a little bit. I'm going to do my best to draw this a little flat. Might not work out so well, but hopefully you get the idea. And here are my carbon p orbitals. And then there's the nitrogen p orbital. That lone pair is not parallel. It is perpendicular in an sp2 orbital. That's why it can't be part of the pi system. But if we look at our other example here, here's our carbon p orbitals. The lone pair for the nitrogen is in that unhybridized p orbital. So combine that with the single electron in the carbons, and we have this overlap, this closed loop of orbitals here. But again, the kind of quick way to judge it is whether or not that heteroatom has a double bond to it. Let's look at another example. This time I'm going to take a look at oxygen. All right, let's assume that this is planar. It's cyclic. Are all the atoms sp2 hybridized? Remember, don't forget about resonance. We can draw a resonance form. That shows that oxygen as sp2 hybridized. So it has an unhybridized p orbital. Now the question is, since oxygen has two lone pairs, how many are actually part of the pi system? And I want you to look at the resonance form there. How many lone pairs actually are part of that ring that got thrown into the ring? Only one of them. One lone pair is part of the pi system. The other is not. And so if I just kind of do all the math, this oxygen contributes 2 pi electrons. Each carbon contributes 1 pi electron. That fits the 4n plus 2 rule for a total of 6 pi electrons. So this compound will be considered aromatic. And if I were to draw a side view of it again, like I did earlier for the other ones, so here's the p orbitals of the carbons. There's the p orbital oxygen, and there's an sp2 orbital there. So one lone pair is going to be overlapping. The other lone pair is going to be in an sp2 orbital. Perpendicular to the system, that's why it cannot contribute to the pi system, because it's not parallel to it. So let me look at one more example, and I'm going to illustrate an important concept here when it comes to, especially when we're doing nitrogen heterocycles, because nitrogens are basic, tend to have make basic compounds. Now, I'm going to ask you one question first. Is this aromatic, anti-aromatic, or not aromatic at all? So let's assume it's planar. And usually on a quiz or an exam or some sort of work, I would let you know, like, yeah, assume it's planar, or I would tell you this compound is not planar. It's cyclic. Are all the atoms sp2 hybridized? Well, this nitrogen right here, and I'd recommend drawing the resonance, is sp2 hybridized, even though it looks like it has 4 regions of electron density around it. I want you to work through the resonance to verify that. Now, how many pi electrons are here? Okay, so let's use our quick rule. If the heteroatom already has a double bond to it, it only contributes one pi electron. Its lone pair, this lone pair right here, is stuck in an sp2 orbital. If there is not a double bond to the heteroatom, then the lone pair gets is part of the pi system. So that nitrogen contributes two, that carbon contributes one, this one contributes one, then other nitrogen contributes one, and that carbon contributes one. So that's a total of 6 pi electrons. That fulfills the 4m plus 2 rule. So this compound is aromatic. Now I want to ask you one more question. Which nitrogen is more basic? Nitrogen compounds tend to be good bases, and this one has two of them, and there's a notable difference in basicity between them. And as you're thinking about this, I want you to think about which nitrogen has their lone pair available to pull off hydrogens. This one at the top, this lone pair, as we said before, is part of the pi system. So it's kind of busy. It's busy being part of the pi system and not available to pull off hydrogens. This one here is not part of the pi system. So it's available to pull off protons. And that's a very important thing that you should know about, especially with nitrogen-containing compounds, is whether or not, first of all, being able to recognize whether or not the lone pair is part of the pi system. And secondly, once you made that determination, be able to identify which nitrogen would be more basic if due to it being available to act as a base.